Okay, so it's a great pleasure this morning to talk to Dr. Chris Copperwheat. Chris is the astronomer in charge of the Liverpool Telescope here in Liverpool, and he's a member of the team that's been doing the study of the planetary system around the star Trappist-1. So, Chris, good morning. Can you tell us a little bit about the star Trappist-1?
Sure, yeah. So Trappist-1, the star, is it's a nearby red dwarf star, an M dwarf. It's an old star, a very red star, quite a faint star, probably just outside of the reach of amateur telescopes on the Earth. So it got its name essentially from its discovery telescope, which is the Trappist telescope. So this is you probably the clues in the name. It's a Belgian-led project. I think the acronym is the Transiting Search for Planets and Planetesimals Telescope, and that's where they get the Trappist from.
Right.
So their idea when they built this telescope, and it's quite a small telescope, 60 centimetres, was to search for planets around red dwarf stars like this one, and we'll come on to why red dwarfs are interesting stars to search around. So the reason it's in the news is this has been a successful search for small planets. So it was discovered last year that this particular star had, they claimed, 3 sort of Earth-sized-ish planets around this star. So there's been much more detailed follow-up there involving telescopes around the world, including the Liverpool Telescope. And so the big announcement this week is that it in fact has not 3 but 7 Earth-sized planets orbiting it.
Okay, so how do we work out the sizes and masses of planets? How do we know that they're Earth-sized? What are the techniques that we use?
It's actually much more simple than you think. It's all really sort of, A-level or, sort of degree-level geometry, essentially. Mm-hmm. So we have the star, and there are a number of ways of detecting exoplanets. Mm-hmm. But in general, the vast majority we've detected indirectly. We detect via the influence of the planet on their host star. Mm-hmm. So a lot of the early exoplanets were discovered by detecting the radial velocity shift, the wobble of the host star as the planet moves around. So this method that we've used for this star is called the transit method, and this has been enormously successful. So essentially you observe the star, and the planet is moving, it's orbiting the star, and the alignment of the orbit is such that it passes in your line of sight, in between us and the host star. So it blocks out a small fraction of the starlight, so you see a little dip if you study it. And then of course the size of that dip, the depth of that dip is related to the size of the planet. So bigger planet, more starlight blocked out, bigger dip.
Okay.
So you've got that to give you the radius, essentially, with reference to the host star.
So you need to know the properties of the host star.
Yes. So the star itself needs to be studied, yes, because essentially you're looking at the sort of relative the two radii. And then you obviously you see the first one, and then you wait for an entire orbit, and then you see the second transit as you see this little dip as the planet transits the disk of the star. And so from that you get the orbital period, the length of the year on that planet, and then it's just a simple case of Kepler's laws and this sort of thing to start working out the geometry of the system, the distance of the planet from the host star and this sort of thing.
So do you see transits from all 7 of these planets?
Yes.
So the same plane.
This is it. Yeah. So the system is orientated essentially almost very close to 90 degrees to us. So we see transits from all 7. So when it was first observed, there were a number of transits. So this is where they came up with the 3. They saw a number of transits, and they weren't sort of strongly. They didn't manage to tie them closely to each other in order to say, right, that's the first one of that planet and that's the second one. And the reason now we know is because there were more planets doing it. And one of them looked particularly weird. There was a very sort of strange shaped one that we realise now was a number of different transits sort of superimposed. So you got a bit of a dip from one star and then another one. So this is what prompted the sort of continual investigation. And the way we unlocked it essentially is by having one block of sort of continuous time where we were looking at the star round the clock to sort of disentangle all this. And a lot of the heavy lifting was done with the Spitzer space telescope. But space telescopes are orbiting the Earth, so they can't stay on it all the time. So it was supplemented by ground-based observing. So telescopes from around the world, including the Liverpool Telescope, we sort of filled in the gaps, and one telescope passed on to the other to get this continual coverage to find all these individual dips and relate, different ones, work out which one's related to which planet.
And the Liverpool Telescope is particularly useful for this because it's very flexible, being a
Indeed, yes.
telescope.
So the Liverpool Telescope is fully robotic. So most telescopes on the ground have large staffs on site who operate it. So the Liverpool Telescope is fully robotic, so not remote control. So we don't sit up in Liverpool and tell it what to do. Basically, astronomers from around the world, they can program in their observations via sort of web-based interface, and then we all go to bed at night, and we get up in the morning, and the telescope has done its thing and presents us with the data in the morning. Right. So there's a couple of advantages to robotic observing. The first thing is we use it a lot for things that are changing very rapidly, where you need to react very quickly, and a robot's much quicker than a human. And then the second one is this, where you want this sort of flexible scheduling, you want sort of automated control to synchronize with other telescopes, and the robot is it communicates itself with other telescopes and other observing facilities, and so that sort of thing is very, very simple. It's very sort of time critical observing.
Right. Going back to the technique,
yes.
So I can see from what you've described how you get the size of the planet from the depth of the dip in the transit. Where's the mass come from? Because we know that these are approximately Earth mass planets as well. Where does the mass information come from? Is it from the extreme precision of the transits?
Yeah, so the key, I think, to unlocking the sort of mass information is to look at the individual sort of the ingress-egress features and the shape of the transit eclipse itself.
Yeah. So there's no spectroscopy in this, so you're not seeing the wobble?
There's no spectroscopy at all,
right.
no.
Right.
So in this case, probably the radial velocity variations, the wobble would be quite small, I'd imagine. Probably on the limit of what you can detect, because these are very small planets. So the transit technique. The radial velocity technique, the reason that was so successful is we discovered very, very large planets very close in, sort of Jupiter-sized planets. So it's when you push down to the Earth-sized planets, the much lower mass ones, this is when methods like the transit technique really become much more powerful.
Okay. So, this is just amazing stuff that we've actually managed to come up with a system of 7 Earth-type planets.
Yeah.
It occurs to me, is there some coincidence here that so many of they really crowd around the Earth mass, very close to the mass of the Earth and Venus? Is anyone suggesting there's something special about that mass, something about planetary formation that?
That's an interesting question, isn't it?
Because there's not a very broad range, is there, in this? Are there any? Can you think of any selection effects? Would this technique? Presumably, it wouldn't. There's a limit to how small a planet it could observe. So there may be smaller planets.
Maybe smaller. Yeah. I mean, my inclination is to think that we're in sort of a small number statistics regime here.
Yeah. Okay. Well, that's the scientists' answer.
Yeah. I mean, the size of the dip, the sort of the transit dip. It's actually quite large in terms of what we can do. So when this technique was sort of pioneered, we were looking at Jupiter-sized planets, and the transit depth was about sort of 1% typically for the sort of hot Jupiters we were finding. So with an Earth-sized planet, that would be much, much, much smaller. And you're then really pushing the limits of what we can do. So this then gets back to why this particular star was targeted. So it was realised that if you actually target a much fainter, smaller star, that then if you have a correspondingly smaller planet, because we going back to how we were talking about how it's the sort of ratio of the radii that's key here. So then you're back in the regime when the dip is around about 1%, and so that was the case here. So the size of the dips were very, very detectable using modern techniques. 1% is fairly sort of trivial to detect that sort of flux change. So we could have detected planets much smaller around, much smaller in radius around this star. Okay. Had we had they been there.
Right.
We can't rule out truly tiny ones.
Okay. Right. So. The big question that a lot of people will be interested in with these: how habitable might these planets be?
Right. Okay. So there's a number of sort of interesting things that go into this, and the big sort of media buzz has been about them being sort of Earth-sized, rocky. So the key thing is, when we talk about habitability, we're always talking about temperature. So, we define a region around the star known as the habitable zone. So the distance from the star, essentially the flux from the star incident on the planet's surface, gives you a handle on the surface temperature. And so what we find is that at least 3 of the planets are in what we call the habitable zone. So the temperature is such that it would be conducive to liquid water. Now I say at least 3 because this is a little kind of a woolly, because when we want to talk about surface temperatures, we're getting a little bit into the question of what the atmospheric composition of the planets are. Yeah. So you can be conservative or pessimistic about the size of the habitable zone. Yeah. So we think at least 3. But it's interesting, because the question of habitability doesn't really end there. I mean, in terms of the sort of popular press, that's kind of the end of the story. And don't get me wrong, these are very strong candidates, but there are other sort of interesting factors that go into this issue, but you have to consider. So the first thing is these planets will be tidally locked. So one side of the planet will be permanently facing its star. Right. So there's going to be a big temperature difference between one hemisphere and the other. Mm-hmm. So how that affects habitability is something we're not very clear about. So the other thing there's been some papers about this recently is the question of the activity, the sort of high energy sort of X-ray activity of the star, how that would affect the planet. Mm-hmm. So M dwarf stars, these red dwarf stars, they can be quite active. There can be a lot of sort of X-ray radiation, extreme ultraviolet and further type of radiation coming from these stars. So this star has actually been studied, and we find it to be about as active as the Earth's quiescent sun. But the planets are a lot closer. Right. So the sort of the high energy flux on the planet is going to be higher. Right. How that affects habitability, we don't know. Right. It's a very interesting question, and you'll see in the literature a lot of different sort of theoretical models. And some, there is a suggestion that this could perhaps strip away the atmosphere, which could be bad. Some theorists have suggested this could preferentially strip away the hydrogen and the helium, which might be good for habitability. It might leave an oxygen, nitrogen atmosphere, that's more like what we're searching for. So from a theoretical point of view, there's a lot of sort of open questions here. Mm-hmm. And the balance always in astronomy and all sciences is the balance between observation and theory. So the next step for us really now is to try and answer these questions about the atmosphere. Because that really then starts to inform the models, and that is the next step. Right. And this work has already started. So the Hubble Telescope is already engaged in a campaign of trying to observe the atmospheres of these planets. Now, how do we do that? So I said the planet moves between us and the star, so the light, most of it is, a fraction of it is blocked by the planet. But you have that extended atmosphere potentially around the planet, so some percentage of the starlight, a very, very small percentage, is passing through the atmosphere of the planet before it reaches us. So if you take a spectrum of the star when the planet is not in front of it, and then again when it is, the difference between those spectra essentially is telling you something about the atmosphere, and you might see either absorption or excitation lines that will tell you what the atmosphere is made of. Right. And that's the next step. And if we were to start looking for the sort of the things like, for example, ozone, that we would associate based on our sample size of 1 with a habitable atmosphere, then things really start getting exciting. Well,
so if you were trying to persuade Elon Musk to develop an interstellar planetary mission, do you think Trappist-1 is now the prime target?
This is now
the Centauri, for example, where we know there's one planet.
Yeah. I mean, so the question I've been doing a bit of press over the past couple of days, and the question people always have been asking me is, where does this rank in terms of discoveries? And I've said it ranks in the top 2 probably. So Proxima is exciting because it's so close. It should be emphasised that this one, so 40 light years is the distance to this system, and from an astronomical point of view, that is still really close. That's in our back garden, you know, approximately sort of 4 light years, so we're talking 10 times further. But this is still really close. And yeah, this, you know, if you were to be talking about, you know, exciting targets for any sort of future, you know, if we were to make some sort of technological breakthrough, it's you know, it's right up there.
Okay. But we're not going there anytime soon, sadly. It's still
not anytime soon. But fortunately for us astronomers, there's still, you know, so much we can do from the ground to study this system. I think so sort of building on that point about the distance. I think perhaps the most exciting thing about this discovery is not the fact that we found this one individual system, but the fact that we have found a complicated solar system with lots of terrestrial planets so close to us. It really does start to suggest that these types of planets are truly common in the local universe, which is an incredibly exciting thing. So when people talk about life, you know, it goes back to the sort of the Drake equation. You have all these different sort of parameters that you tweak, and they're all sort of unknowns. You know, how many planets are there, and then how many of them are the right temperature, and then how many form the various sort of, you know, biomarker stages that you need. You know, these are all percentages you multiply along to get some sort of probability. And so we're starting to actually put limits on those early numbers. So we in the past 20 years, the field of exoplanets has grown from nothing. So when I was at school in the 90s, we knew of no exoplanets. And now we know of thousands. So the question about, are there planets in the universe? Yes, lots, extremely common, you know, tick. So now we're on the next one, you know, how many of those are sort of, you know, terrestrial, sort of rocky type planets? And this seems to be saying that there are lots. So that's another one. So even if this is a totally sort of barren system with no life at all, the overall probability of finding life, this is a big sort of uplift to the calculation, I think.
Right. I think that's probably a good point to finish on. So thank you very much for talking to me.
My pleasure.
Okay.